Dr. Luke Barnes is a lecturer in physics at Western Sydney University with a PhD in astronomy from the University of Cambridge. The focus of his research has been the cosmic evolution of matter, and he has published papers in the field of galaxy formation and evolution and on the fine-tuning of the universe for life. He is the co-author with Professor Durant Lewis of A Fortunate Universe, Life in a Finely Tuned Cosmos, and that is published by Cambridge. He also wrote The Cosmic Revolutionaries Handbook, so those are great books. Please welcome Dr. Luke Barnes.
I can go there. This goes on. I'm loud enough anyway, but am I actually? Okay, good. Well, good morning, everyone. Hello. It's good to get to know everyone. Who came the furthest to be here? Me, I did. I came from Sydney. So it's wonderful to be here. Thank you so much to Paul. Thank you to everyone who's organised this conference. I'm having a great time already. And a special thank you to whoever put an astrophysicist on at 9 a.m. on a Saturday morning. So it's going to be all right. Part of the reason it's going to be all right is that I have the best PowerPoint slides, okay? As an astrophysicist, as an astronomer, I win this game every time, okay? It's very, very easy. We could do this all day. How many of these do you want? We can just look at what the James Webb Telescope has shown us about the universe around us. I could just do this for an hour. Do you want to do this for an hour? No. But I'm here actually to talk about the fine-tuning of the universe for intelligent life. There is something about our universe which is amazing. There's plenty of things about our universe that are amazing at every level. So if you're here at Apologetics conference, I assume you've already sort of at least heard the outlines of the fine-tuning argument. There's something particularly amazing and weird going on down at the level of the fundamental constants of nature. What I want to really talk about today is where does this argument fit in terms of equipping you to go out there and actually use it in the real world, in your sort of BAT utility belt, where you've got all the bits and pieces of the historical this and the argument from that. Where does fine-tuning fit in? And one of the things that makes fine-tuning particularly interesting, I suppose, and particularly arresting, is the fact that it was almost stumbled across by accident. What happened was that a number of decades ago, physicists accidentally asked the right question. So, let me explain. Before I do that, let me just make sure I keep an eye on the time. I've discovered as a public speaker, no one cares if you take the time to show the audience that you actually care whether you finish on time. Okay, good. How physics explains. My job, I'm an astrophysicist. My job is to take those, let's go back to these. Yeah, let's look at that for a while. To take the things that we find in the universe and try to work out how they work. In what way are the physical forces that shape our universe coming together specifically to make the things that we see around us? An explanation in physics will involve these three ingredients, typically. So, for example, first of all, there are the laws of nature themselves. There are laws like the law of gravity, electromagnetism, that tell us how the parts of the universe interact with each other. Secondly, there are the initial conditions. The laws of nature don't tell us how the universe is. They tell us how the universe changes. So if you want to know how the universe is, the laws will help you, but you also need to know something about how at least the system you're interested in, how it started off. So for example, if you want to know where all the planets will be in the night sky tomorrow, you need to know the law of gravity, but you also need to know where they are tonight, because the law of gravity itself won't tell you where Mars is. So there's those two components, but there's a third one. In the laws themselves, there are these things called the fundamental constants of nature. What we want from our physics is to get numbers out of our model. So, where will Mars be in the night sky tomorrow? I want that to come out of the model. I don't want to have to put that in by hand. That would just sort of defeat the whole purpose. I'm trying to make a prediction here. I can't just, write the answer in. But there are some numbers that we need to put into the equations before we start. So, if you have any recollection of high school physics, and if you don't, look away now, there's a number in Newton's theory equation of gravity, the big capital G, G for gravity. Right? It has a certain value, which you can go and look up. That's a fundamental constant. The theory doesn't predict that number. We don't get it out of our equations, we have to go and put it in. Now, why should we be interested in these numbers? Well, once we've got a pretty good handle on how things work in the universe, these numbers are right there at the base of the sort of explanations of what's out there. So, for example, yes, there will be an exam later on, so please take some notes. If you break the stuff of our universe apart into the smallest pieces we've found, all the stuff that you're made out of boils down to these three Lego pieces. They are the up quark, the down quark, and the electron. No one seems to be writing that down. Up quark, down quark, electron. Look, there might be a trivia quiz at some point in your life where that helps you out. Okay, the Lego set of our universe has three pieces. Up quark, down quark, and electron. They have some fundamental properties, but it's a fairly short list. So they have a certain electric charge, they have a bunch of other numbers that would take me an awfully long time to explain, but they're just a couple of numbers, and they have a number, for example, their mass. How heavy is an electron if you put it on a really, really small set of scales? We know these numbers. The reason why these particular fundamental constants matter is because, again, we're made out of these things, and so changing their properties affects the way the universe builds on its fundamental building blocks. So, for example, suppose I give you the assembly line of the universe. Right? We're in a factory, we're going to build some interesting stuff. So in at one end of the production line comes up quarks, down quarks, and electrons. What can you build out of those? Well, step one would be you can build protons and neutrons out of the up and down quarks. Those groups of three, two ups and a down for a proton, two downs and an up, if you want to try this in your kitchen later on. For a neutron, will give you those familiar particles. So that's the next step onwards in our production line. And then that goes on to the next person. All right, what can you make out of protons and neutrons and electrons? Well, you can make, first of all, nuclei, the centers of atoms. So you can put protons and neutrons, they will stick together in various forms to build the nuclei at the very center of atoms. The electrons will go around the outside. Okay, how many options are there for that particular process? Well, however many protons you put in the center, that tells you which of the elements in the periodic table you are. I've made the periodic table really small here just so you don't get flashbacks of chemistry. It's going to be all right. So that I'm definitely not going to ask about chemistry. These are all the different ways you can put protons and neutrons together to make a nucleus to make different types of atoms. So there's the next step in our production line. Well, all right, with all of these elements, what can you make? Well, it turns out if you put nuclei close to each other, the electrons will run not just around their own home nucleus, but around the whole collection of things. So these outer electrons won't just go around the one nucleus, they'll go around the whole thing, and they'll bind it together so that you can make chemical bonds. And that, in about 2 sentences, is chemistry. It's not that hard, right? So our universe, it turns out, so we're on the production line, we've made simple chemical bonds. Our universe is really quite good at this, because if you get ambitious, you can put this combination of things together. That's DNA. If you take those elements, hydrogen, oxygen, nitrogen, carbon, and phosphorus, and put them in that order, you can literally write the instructions for a person. What they are specifically writing the instructions for, as you move along on the production line, is the basic proteins that make up cells in a process which is now way outside of my expertise. So I'll just wave my hands and say this happens somehow. and then way outside of expertise, if you put enough of these cells together, you can make people. And there's an awful lot going on in that little arrow there. So at the end of the production line, there we are. It's one of the major questions of, life and existence and all those things. Where am I in the scheme of things? Well, from the bottom up in physics, the story goes a little bit something like that. So, if we go all the way back to the start of the production line and look at those basic pieces again, we might wonder, why do those numbers, remember those constants, like the mass of the most basic bit, the electron, say, those numbers, why are they what they are? Why do they have that particular value? And again, the theory won't tell you because it's not a prediction of the theory. But you could ask the following question. The sort of question you ask all the time in physics. Whenever you have a model with some numbers in them, parameters in them, you wonder what happens if I change the parameters. Well, we can do that with the fundamental constants of nature. What if the constants of nature had been a little bit different? And that's a perfectly normal question to ask in physics. But in this case, because these are the fundamental constants of nature, there's a lot riding on the answer because we're made out of this stuff. So, let me give you a bit of a tour to what happens if you start changing some of these numbers. What we're going to do is look at the consequences of making seemingly small changes to the fundamental constants of nature. I'm going to leave that there. Remember, there were three basic building blocks that you're made out of. Perfect, yes. You all just for the record for the video, everyone in complete unison said up quark, down quark, and electron. With one voice. That was beautiful. All right. They've got, that was great. I'm going to try that again sometime. There's three numbers then. How heavy are these things? Now, they're very small numbers in any sort of reasonable human-sized unit, like a pound or a kilogram or whatever you prefer. But we know what those numbers are. So if you've got three numbers, mathematically at least, I can represent that as a point in a three-dimensional space. So in terms of the possibilities, I can represent our choice there as a point in a three-dimensional block. So think of this as a menu. What kind of universe would you like? Okay, so there's whichever number you choose for the up quark, that's that axis, down quark, that axis, electron, that's that axis. Now, in order, just a little bit of nerdery for those who are interested, these are logarithmic axes. In order to fit things in so we can see what's actually going on, rather than going linearly 1, 2, 3, 4, 5, you go in factors of 10. So you go up 1, 10, 100, 1,000, etc. That's a very widely used sort of mathematical helper for us to see what's going on when there's lots of orders of magnitude involved. But in case you're lost at the moment, here you are. Here's our universe. That's the choice that we made. Well, we didn't make it. That's the choice our universe made somehow. There's a limit at the top here, by the way, because beyond there we don't actually have a theory that can tell us what's going on. If you make a single particle too heavy, our theories lose the ability to tell us what would actually happen there for various reasons I can go into. There's a limit at the bottom which is even more technical, so we'll get that. But in between those, there's a good 60 orders of magnitude where mathematically everything is fine. Right? You got some equations of physics. You have a lovely afternoon. You say, what if I change these numbers? And mathematically everything's great. But in terms of the way the universe turns out, some of these universes are going to actually be pretty boring in the following sense. Not much is going to be able to happen. That whole production line that I talked about, where you start with the basic building blocks and physics, nuclear physics, chemistry, biology, people, that whole story is going to get cut off at some point. So let me help you out. Here's the menu. I'm going to chop bits off the menu if they're going to result in particularly boring universes. So, I've chopped off 2 bits around the back there. What happens in those universes is if we think back to the production line, electrons, up quarks, down quarks. The next step doesn't make protons and neutrons, it makes other particles known as the delta plus plus or the delta minus, depending on where you are. And definitely no one's writing that down, that's fine, I understand that entirely. In short, if you ask what's the most stable thing in the universe, it's the lightest thing that you can make out of these particles. Anything heavier could decay. That's a long story short. Over here, if you have quarks, the thing you can make out of those, which will still be there tomorrow when you go and check on it, is 3 up quarks stuck together. Here's why this matters. The production line in that universe goes like this. If you're over in this section here, is up quark, down quark, electron, and then the delta plus plus particle, and then you could put an electron around the delta plus plus particle, and that is the end of the story. Because nothing else in the universe will stick to anything. What we needed next was to sort of start building up the sort of hierarchy of this sticks to that, and I put some of those in, and I stir it and put it in the oven for a while, and whatever else has to happen. The story in that universe ends here. This is the most complicated thing you can make. There's one particle with another particle going around the outside. In fact, an even smaller sort of sliver off the side of that, and you get universes that do the following. So here's where most of the special effects budget went in this talk, so just enjoy this. Here's a very simple picture of an atom, right? So there's a nucleus. In this case, there's 1 proton, 1 neutron, and an electron going around the outside. Points if you know that this is deuterium. There's no sign of quantum mechanics here, by the way, which is helpful. What happens if you start messing with these numbers? Well, it's actually quite easy to make it so that the proton and the neutron, or whatever the smallest things you can make, don't actually stick to each other. In that case, this is all you can make. Actually, you can make universes where it gets even worse than this, where the electron, instead of going around the outside, spirals into the nucleus and just makes a neutron. These universes, these aren't great. Here's why. So here's the periodic table. This is, by the way, this is the astronomer's periodic table. It's the little images are where that particular element gets made in the universe. So are you made in big stars or small stars or the Big Bang? Or anyway, you can enjoy that for yourself later on. What happens? Remember, we're doing the what if game, right? We've got our production line, and I went back to the start of the production line and I messed with a couple of dials over here. What happens in a universe where you've messed around with the masses of the fundamental particles? Well, it's very, very easy to make a universe where the periodic table looks like this. Now, I should say, that slide is actually a sort of a very mild form of protest. Yeah, they made me convert my Keynote file into a PowerPoint file, and so I, in response, chose the most obnoxious slide animation, so I think I succeeded there. In this universe, that's the periodic table. So, how to put this? In that universe, the chemistry exam goes like this. Question 1, what is the element? Hydrogen. Good, well done. Question 2, what is the chemical reaction? There's only one. You can put 2 of them together to make a hydrogen molecule. And that is the end of the exam, because there's nothing else to ask. There's nothing, that's it. These don't stick to each other particularly well. There's nothing else you can make. In our universe, if you look up sort of online chemistry databases, there are tens of millions of known chemical compounds of ways you can put the 92 known naturally occurring elements together to make compounds. In that universe, that whole database goes away except for one entry. Not tens of millions, one. That's the sort of thing that happens once you start messing around with these fundamental constants. Right? These are the ways that things stick together. And so if you get that wrong, things don't stick together. There are a number of other constraints we can do. I've illustrated one of them. The short story is that by the time you get to the end of this story, that whole menu gets whittled down to this very thin slice, where if you don't land there, nothing much interesting happens. And on a very sort of obvious scale, how many different elements are there in the periodic table that actually get made in most of this space? The answer is 1, maybe 2, maybe none, if you only have neutrons. But for this one beautiful little strip here, the answer is 92, and I can make DNA and people. It'll be great, wonderful stuff happens. But that only happens if you get these numbers right. This is the picture of the fine-tuning of the universe for life. We started for very straightforward, obvious physics reasons, asking the question, what if these numbers have been different? And no one quite knew what the answer would be before we started, and the answer turned out, well, it's really, really easy to ruin a universe. This applies on larger scales as well. There's one of the limits in here is, can you make a gravitationally bound object, something that will hold itself together with gravity, which lives long enough to provide energy? So we know of these as stars. So if you go outside and look at the sun, you'll burn your eyes out. Don't do that. But if you take the right sort of video with the right sort of filters, there's the surface of the sun. Stars are actually remarkably physically simple. You can write down the equations about how they work and their structure and how long they live and all that sort of stuff on the back of an envelope, which is great fun. The short story is, as in all things in astrophysics, you have to ask the question, what's holding back the force of gravity? Because it's always attractive. So you have a whole bunch of mass here in the star. Gravity, represented by these blue arrows here, is trying to crush the whole thing towards the center, but the sun, thank goodness, is not being crushed completely. It's holding itself up. In this case, why? Well, because there's heat. There's ordinary pressure forces. They are holding the sun up. But we can play our game again. What if I go trying to ruin the universe? What if I start changing the laws of nature? Well, not the laws, the constants of nature. In this case, it turns out remarkably easy to make a universe in which this standoff between these forces, rather than being in the sun a nice standoff, where if tomorrow gravity sort of collapsed the sun a little bit, the heat forces would push it back to where it was, or if it expanded a bit more, gravity would bring it back. It's sort of a nice standoff where no one's really trying to push the boundary. You can make stars where whenever the star collapses a little bit, it overcorrects. And so you get stars that oscillate wildly and eventually blow themselves to bits. We see stars like this in our universe, but it's only the very heaviest, the most massive stars that do this. Change the fundamental laws of nature, change the fundamental constants of nature, and you make all stars like that in the universe. Anything big enough to burn is big enough to blow itself apart. One more example, just for fun. Let me go. This is a supercomputer simulation of how galaxies form. If you, in the context of an expanding universe, you code your understanding of the forces of gravity and how stars form and all these sorts of things into a supercomputer, and then you run this simulation for a month and a half and hope that nothing happens to the computer for that month and a half. It's several thousand computers all networked together. You have the history of the universe play out on your computer. The short story here is that from a very smooth beginning to our universe, if there are any bits of the universe more dense than average, gravity will make those parts of the universe grab onto more things around them, and so basically the rich get richer. And so the dense bits of the universe get even denser, and that's how structure forms in our universe. So that number there is, by the way, is the time since the beginning of the universe, so that was the fastest fast forward you've ever seen. Why don't we run that again just for some fun? There we go. Okay. So, if you tried to do this on your laptop at home, it would take you 500 years. So you don't do that. You get a supercomputer to do all this stuff. Once again, we have a sort of a factory line. Right? If you take the basic stuff of our universe and expanding space-time, stuff that's almost perfectly smoothly spread around the universe, and you let that be shaped by the passage of time and by the operation of the laws of nature as we know them, the universe forms these structures. Gravity will bring things together into galaxies. Inside of galaxies, stars will form. Around stars, planets will form. And the structure that we rely on here in our universe ends up, all there at the end of the day. Well, most cosmologists who do this work, what you do with a simulation like this once you've done it is you go and compare it to our actual universe to see whether you got the answer right. And inevitably the answer is, yes, sort of. Some of the details are right, some of them aren't, and then you go and try again. And it's great fun. What we did, some colleagues of mine at Durham University and a few other places, was we said, let's take this exact same code, the same computer model here, actually the same supercomputer as well, incidentally, and let's change some of the fundamental numbers of the universe and see what happens. And here's the answer. When I hit, nothing's happening yet. Once I hit play on this, there's going to be 3 panels. On the left is roughly our universe, right? Where an initially simple state turns into complexity later on, galaxies, all the stuff that we rely on. In the middle and on the right will be 2 alternative universes, not our universe, but where we've changed one number. That number is known as the cosmological constant. The short story of the cosmological constant is we discovered in 1998 that the expansion of our universe is accelerating. So the universe is not just getting bigger, it's getting bigger faster and faster. So if you spot a galaxy over there somewhere, we've known for about 100 years that it, on average, will be moving away from us. It'll be redshifted. What we've known since 1998 is it's moving faster today than it was yesterday. The reason why that's happening is still a major unknown, but we at least know the sort of strength of the effect, if you like, and we sort of codify that number in the cosmological constant. It's the number that's responsible for the accelerating expansion. So, if we start changing that number relative to what it could be, what happens to the universe? Well, remember the whole way that structure formed was gravity sort of grabs on the nearest things and pulls it together to make a galaxy. This is rather important. The air in this room is 1 billion times more dense than the average density of the universe. The air in this room is 1 billion times more dense than the average density of the universe. If you go pick a typical place out there in the universe and say, how much stuff is there in a sort of cubic meter or whatever, units you want to use over here, the answer in this room is per cubic meter is about 1 kilogram of air. Typically out there in the universe, there's 1/1000th of 1/1000th of 1/1000th of a kilogram of stuff out there. In other words, if you start with a universe that's almost perfectly smooth as ours did, you've got a bit of work to do if you actually want to make some interesting places in the universe where there might be things like air and solids and liquids and potentially life. So this whole process is rather important to us. So what happens? What if I change that number, that cosmological constant number? Well, the universe starts off almost the same because its effect doesn't kick in till later on. The initial conditions are almost the same. But because this is pushing everything away from everything else, what you'll see in the panel on the right is everything starts getting a long way from everything else. That process of gravity grabbing a hold of things and making structure form shuts down quite quickly. And so you do actually make a few sort of very small galaxies and stars, but the whole process doesn't last very long. In the middle, some galaxies form before the acceleration takes over, but they are very soon isolated and very empty, whereas in our universe, you can see structure all over the place. Now, I'm going to play that again. Good. Now, I'm going to play this again because this took ages, so we're just going to appreciate how much effort this took. This was several years of my life. Okay. Yeah. We're in the nice one that does the interesting stuff. Very small changes to the constants of nature ruin the universe. So, here's a summary. Of the possible values of the fundamental constants of nature, the subset that permit the existence of life seems to be very small. It's really easy to mess up your universe. This is the case that we made, that's been made for a number of years, but we made specifically in A Fortunate Universe, a book that I co-wrote with Geraint Lewis. Geraint's an atheist and a Welshman. One of those is shocking, but anyway. For the first 7 chapters, we wrote them together, and apart from one footnote that you can go and find yourselves, we agreed on all the science. As I said, physicists accidentally started asking the right question. All of this stuff, a lot of the broad details of this were worked out simply in the ordinary sort of progress of physics. You just want to know what happens if these numbers have been different. And so this is an area where actually a Christian and an atheist can write a book about the science here and agree about basically everything. Then comes chapter 8, where we try and work out what all of this actually means. So as you might have guessed, there is also, as well as the physics literature, a sort of strong philosophy literature on the fine-tuning argument for the existence of God. If you want to follow this up later, here are some names for you to look at. Oh, now we're writing it down. No electron up, quark down. Sure, fine. I'll let you take a photo of the screen on that one. My apologies if I'm missing anyone, but there are some names. So, can we turn this into a good argument for the existence of God? Here are some people who've tried to defend that. I've had a crack at it myself. My favourite summary of the fine-tuning argument goes a little bit like this. I'm not religious, but something weird is going on here. That's a pretty good summary. I think, I still need to check this, but I think someone said that to Alistair McGrath after he gave a talk about fine-tuning. I'm not religious, but something weird is going on here. Can we turn this into an argument? Here's the way I want to formulate it. After sort of years of talking to about this with a whole bunch of people, here's where I think this argument fits in. On one level, the design argument doesn't really need to be an argument, does it? Hopefully you can see the connection with this on screen, right? I mean, if I show you that and you don't see design, like, I can't help you. I mean, I think possibly my phone had listened to me make this point before, because shortly after I started showing this image, this particular video in talks, Facebook started to try to sell me this. I haven't got one, but I am very tempted. I mean, so this is the oldest, argument for God there is. It's not even an argument, it's just an intuition. That looks well put together. That thing doesn't even fly. The other one actually flies. It's important that this is not in any way, it's not really controversial. The question is not whether there is a design intuition, the question is what you do with it. So Richard Dawkins in The Blind Watchmaker says, biology is the study of complicated things that give the appearance of having been designed for a purpose. Physics is the study of simple things that do not tempt us to invoke design. He defined biology as the study of things that look designed. Not just an incidental feature, but the definition of biology. But he's hoping that if he can take biological processes and show how they come out of physics processes via evolution or whatever particular process he wants to talk about there, that'll be the end of the story, because he's hoping physics is the study of simple things that do not tempt us to invoke design. Which makes a very important point about the status of evolution and the design argument. It's not solved, it's moved. And Dawkins, of course, is a biologist. I don't want to start a turf war. Sorry, I said that wrong. I do want to start a turf war. It's a physics question. If he's put all his hope in, if we look really hard at physics, we won't be tempted to invoke design. The thing to do next is to look really hard at physics. What he's hoping is that when we look really hard at physics, we'll find that actually the simple stuff of the universe won't look remarkable, right? Are the fundamental physical processes that shaped our world, are they boring and unexceptional and unremarkable and typical? Right? No one's going to say that about the hummingbird, but if you can at least say that about the stuff the hummingbird's made out of, you might hope that the design intuition will go away. What's interesting about Dawkins, if you read Blind Watchmaker in the first chapter, there's actually a method there. When he says the appearance of design, what's he sort of pointing to? What feature of these things shows design? So here's a quote from Dawkins. It is true that there are quite a number of ways of making a living, flying, swimming, swinging through the trees and so on. But, however many ways there are of being alive, it is certain that there are vastly more ways of being dead, or rather not alive. You may throw cells together at random, over and over again for 1 billion years, and not once will you get a conglomeration that flies or swims or burrows or runs or does anything even badly that could remotely be construed as working to keep itself alive. In other words, why do we think that there's design in biology? Well, he says, here's a way to pump your intuition in case you needed it. What happens if you throw cells together at random? And the answer is, you don't get something that flies. But there's a method there. We just need to apply it down at that level that he was telling us to go and look at. What happens if you throw a universe together at random? What if you throw the universe in a blender and start changing these numbers? Well, a useful way to answer this question, one that we can actually calculate rather than just guess, is to start randomly changing those constants and initial conditions. You could think about randomly changing the laws of nature. It's just harder to do and harder to do systematically. We have a chapter in the book on that, but it's not straightforward. But we can be systematic about the constants because they're just numbers. There's a finite number of them, 31 to be exact. We can just say, what if those numbers had values consistent with the equations, but otherwise just at random? And the answer, as I hopefully have shown you, is the universe doesn't fly. Nothing works. Nothing sticks to anything else. And even if it did, it would fall apart immediately. Our universe is in just making atoms and chemicals at all is doing something remarkable and rare. Does physics tempt us to invoke design? Yes. Long as you ask the right question. This was why it was so important that physicists accidentally started asking the right question. All of this stuff about what happens if you change these numbers wasn't asked in order to sort of test design theories or do, apologetics or anything like that. It was just asked by physicists doing their job. It's in the physics literature, it's not in the theology literature, right? You just do these calculations. But at the end of that, you found you've accidentally asked exactly the right question to know whether there is design down at the bottom. And the answer is that the impression of design follows us as deeply as we can do science right now. What happens, however, if you keep doing science, right? Which we will, thank goodness. I still have a job. Phew. This leads us to the multiverse. And I'm just about ready to wrap up and I'm leaving time for questions. Good. You'll be familiar with the multiverse if you're familiar with fine-tuning arguments, or if you're familiar with Spider-Man. Perhaps the universe is like a lottery. Yes, it's very unlikely that any given ticket will win the lottery, but if lots of people buy different tickets, then someone somewhere, it's more likely that someone somewhere is going to win. Maybe the universe is like that. All these numbers, you've got to get your winning lottery ticket to have life, but what if there's lots of different universes out there, each with their own lottery ticket of constants? What if that's the way our universe is? Now, the important thing about this is there's two separate questions here. One of them is that idea actually true? That's a perfectly good question to ask. Can we test it? We can go that way. The answer is there's not a lot of evidence one way or another. But there's also the question, does it actually remove the design intuition? Remember, the question was not whether physics explains the universe. The question is whether physics looks designed. So the question is Not if we keep following down the levels, we should have to ask this question: what happens if you throw a multiverse together at random? Not just is there one, but what happens if you throw one together at random? Will we be tempted to invoke design when we look at the physics of the multiverse? And here's where the problem is. We have absolutely no idea what the answer to that third question is, because there is no standard model of the multiverse. All these other physics I'm talking about, these are called the standard model of particle physics and the standard model of cosmology. And they explain a boatload, technical term, a boatload of data. Right? There are no multiverse models like that. We have a bunch of toy models, sort of half ideas, things to try and think about. But we just don't have a theory where we could even pretend we know what the answer to that is. Which means that this objection to the fine-tuning argument is really sort of trying to throw the question so far away that we can't see where it went, if you want to put it that way. It's taking your bat and ball and going home, right? It's refusing to play the game anymore. So there's an introduction to the fine-tuning argument. When is this thing particularly useful? If you've got this in your belt to some extent, when's it going to sort of come out? So here's a couple of things to think about with regards to that. First of all, I've seen this sort of presentation have an enormous impact on people who know an awful lot about physics. One of the things that tipped me off to that there's something going on here with this fine-tuning stuff. I'm not weird, but I'm not religious, but something weird is going on here. I am weird, sorry, but I'm not. I was at Sydney University as a postdoctoral researcher. This is about 10 years ago. And I'd written a review article about fine-tuning. And my department, the Institute for Astronomy, said, we've got a seminar slot. Do you want to talk about all this stuff? And I said, it's pretty weird stuff, but all right. Now, the way the usual astronomy seminar goes is there's an hour, talk for about 50 minutes, leave 5 minutes for questions. Questions are usually done in about 2 minutes, and then everyone has lunch. That's the way a usual one goes. And I thought, I bet there's going to be questions. I'll do 45 minutes to leave, 10 minutes for questions at the end. Questions went for an hour and a half. Never seen anything like it before or since. Nobody left, nobody moved. We all had to sit there. Everyone had immediately an opinion about this. Professional astrophysicists and astronomers. Everyone had an opinion, like, we have to do something about this. A couple of years later, I was doing a Skeptics in the Pub talk in New Zealand. And it was a room full of skeptics in a pub, as promised. And I gave basically the sort of presentation here, roughly along those lines. Was very clear to mention that my co-author is an atheist, so they could just write me off as some weirdo Christian. And what happened afterwards, again, was amazing. It's not just they had lots of questions for me, but questions coming at me were intercepted by someone else. Everyone thought that we have to say something about this, but no one could agree on what the right answer was, other than it definitely wasn't God. That they were all agreed on. But it was great, and I really hope this happens to you one day. It was one of the most enjoyable experiences of my life. The room started arguing with itself about what this means. What do we do with this? This is something very awkward if you're a skeptic in a pub. It has that effect. This is something really quite weird, right? One of the things that makes it particularly arresting is that it doesn't at any point, the fine-tuning argument doesn't at any point argue that a particular scientific theory is wrong or at odds with the data or empirically inadequate or anything like that. There's no point where I say, well, this idea is wrong, therefore there's a God, which is what I think a lot of atheists are used to once Christians start talking about science. Right? What they're really there to do is to sort of give science a great big kick in the hope that God will come out the winner at the end of that. I'm going to talk a bit more about that this afternoon in my breakout session. But what I really think the advantage, and I'll finish on this point, is for the fine-tuning argument, is that it reconnects us with our intuition. If you see design in a hummingbird, you've seen design in the universe. If you're worried that physics, the deeper physics, that the progress of science will take that away, what fine-tuning will do is say, no, that impression will follow you as deep as science has gone into the inner workings of our universe. And what that should hopefully do is return you to where you started of just being absolutely gobsmacked at the things you see around you in the natural world. It vindicates our intuition. That response you have, and I hope you've had it, whether it's to the smallest things like a hummingbird, whether it's to the night sky, please go out and see the real night sky at some point. What fine-tuning does is it reconnects us. That first impression you had of this place is amazing is vindicated all the way down to the bottom of physics. Let me finish with this quote by a very famous physicist, Henri Poincaré, in 1905. "We should be astonished at nature's regularity. Men demand of their gods to prove their existence by miracles, but the eternal marvel is that there are not miracles without cease. The world is divine because it is a harmony. If it were ruled by caprice, what could prove to us that it was not ruled by chance?" And I'll finish it there. Thank you very much.
All right, we've got about 10 minutes. Please keep your question as brief as you can so we can get as many questions as possible. So who wants to go first?
Thank you for this. It was interesting that you said the chemistry is real easy for the stars, you know, and even that early model, when you take gravity and the mass and how that can come about. But my understanding is that with life, it's so much more complicated, and that there's all of the chemical interactions that are required to create like the dual-strand DNA. There's just not enough time in this one universe we know about in the multiverse for this even to, I've heard this argument made, that there's just not enough time for life to just kind of happen. And so, and it kind of reminds me of the amino acid experiment where they're able to make it one amino acid with lightning and some chemicals, but nothing since then has ever been done for 60 years, in fact. And I guess, so my question is, to me, and I guess one last thing, it suggests to me life then probably degrades over time, perhaps. Anyway, it's so complicated to just maintain it. There may be little small evolutions, but I guess my question is this. Would you entertain the idea that in the Bible that there is this such a thing as a young earth and for that matter, a young universe? In other words, all these constants do apply, but the designer also set in motion these things not at some point 14 billion years ago, but 6,000 years ago with all of these, it's almost like, I don't know if that's a constant, but basically having the start date be 13.7 billion years ago or whatever it be.
So, let me just sort this out once and for all. Let me answer it this way. Here's how to defend this argument if you, unlike me, are a young Earth creationist. It's basically I don't know if you did debates in high school, it's the even if sort of tactic. Like even if I give the naturalist all the theories that they think are right about the universe, the standard models, is there still a good argument for design there? And fine-tuning shows, yes, there is absolutely a good argument there. So if you're doing this argument as a young Earth creationist, you can do the particle physics stuff about what happens if you can ruin chemicals, that's fine. You could say, look, even on the Big Bang Theory, it looks like there's design there, even though I don't think that that's a correct theory of the universe. And this argument doesn't really have any sort of, it just doesn't make a wager one way or the other about the origin of life. It's just that's a separate sort of topic. That's not where my personal opinion is about age of the universe and all that sort of stuff. But there's plenty to get on with here if that's your sort of perspective on the universe. You can make good use of the fine-tuning argument.
Hi. So sometimes what happens is when I discuss, when I've talked about this argument with skeptics, it's they'll ask something like, oh, well, how do we know that, when and we change these, we change these constants, like things will be like this or be like that, and the problem for me is that often when I try to get it into the literature to kind of explain that, including your work and your lectures and whatnot, it often winds up going over my head. So I'm wondering if there's maybe an explain it like I'm five version that I can use.
So how do we know what would really happen if these constants were different? And the answer is because I can do my job. I'm a theoretical astrophysicist, man. That's my job. What would happen if a physical system were described by these equations? If I can't do that, I'm out of a job. That's exactly what we do. It's what theoretical physics does. What are the consequences of this mathematical model of the universe? And then you go and see whether you were right. That's the other bit of physics, right? So it's important to see how radical that skepticism is. Oh, you can't really know what would happen if these numbers had been different. It's amounting to saying we can't do theoretical physics. And I'm pretty sure I can. I've done it before. It went all right. So I think that's sort of part of my answer to that. Like, this is not something completely weird and outside the bounds of normal physics that we're doing here. As I said, this was done before we knew it had any implications about fine-tuning or anything like that. You just change the numbers and see what would happen. So I would stress that point that this is, a lot of the ingredients for the fine-tuning argument are already there in physics, right? You don't have to do much sort of bringing in stuff from the outside. Hopefully that helps.
Hi, thank you so much for your presentation. This was amazing. My question was, and I've had this problem, you talk to so many people that have these grand ideas and have all of these arguments, but how do you transfer that in your personal life to the physical gospel? Because you're bringing up these ideas that make them question and make them turn to their intuition, but do you have any stories of when that turned someone towards Christ?
Yeah, that's great. That's a great question. The first thing to say is, you see in Romans 1 that there is a sort of, there's something about nature that we all sort of confront, but that doesn't necessarily lead people all the way to Jesus. But it's not nothing. So I think, this is when do I pull it out of my bat belt, right? It depends where people are. If you've got someone who thinks that the idea of God is completely ridiculous and totally opposed to science, this might be something that could at least sort of confront them with that. Because if you've got someone in that scenario, if you say, hey, Jesus rose from the dead, right? If you start talking about miracles, they think the weight of science is against that. Now, you could go and talk about that separately. But, in terms of how do you lead the conversation towards Jesus, I think the answer to that is, look, if you, as a result of thinking about design in the universe, get the impression that it's worth taking seriously the idea that there is a mind behind the universe, that should be enough for you to move the question of could a miracle happen out of the absolutely no way into the, well, there'd have to be good evidence, I suppose, and then go and read the Gospels, because there's someone in there. Right? And it's at that point, right? I'm a physicist. I can't derive my way all the way to Jesus, but I can point in the right direction at least. So again, this is where, I'll put the little thing in your bat belt, and you see how you can go and use it out there in the universe.
Yeah, I have a question on science. So you have our universe, and our universe is so fine-tuned. If our universe is so fine-tuned, how are multiverses possible? Are other universes really simple? Would there be possible histories for those other universes?
Yeah, so it's important to remember, if you're thinking about the multiverse objection, there's not really any such thing as the multiverse. That's a name for a group of ideas that range from sort of extensions to the standard model of physics to, Spider-Man, right? What if there were other universes out there is about as much as the multiverse as a label specifies. What should happen next? As I said, I'm a theoretical physicist. If I'm going to take this idea seriously, I want equations. I want to know initial conditions. You got to start specifying some stuff, and that's not really happening particularly convincingly in the physics literature. Right, that's one of my main sort of concerns with the multiverse. Basically, all those questions you have aren't specified by saying, hey, there's a multiverse. You have to do some more physics, do some more specification, do some more, well, here's exactly what my idea is. You know, you turn the handle and a crank in a universe, whatever. Right, that's where you should be specifying those ideas.
All right, let's give Dr. Barnes a hand. Unfortunately, we're out of time. We'll leave that.